So it sounds like a tradition also. We are bringing people also from the other side, from Torino, it seems, but he's the second one this month. Alain was doing the PhD in École Normale Supérieure in Paris. Then after that, he did the postdoc in the ICTP in Dresden. He was, after that, seeing in Marseille, in Paris for some years, and more recently he moved to Marseille. So let's say, whether similar to ours here, also in the Mediterranean. I do like that kind of things. So, he has been working a lot on complex systems, complexity in general. So probably you know some of the works or him personally. So this is why it's nice to have him here. He will be here until Friday. So if anyone wants to meet at, he's upstairs in the 103. Okay, so just go and talk to him. And well, he will be presenting a work about diseases in cows in this case. So it's a nice application for epidemiology of the concept of complex networks and disease propagation that has been working for quite a while. So well, it's a pleasure to have you here.
Thank you, Jose. Thank you for the nice introduction, and thank you especially for the invitation. And I've been aware of this institute for a long time, but it's actually my first time I was visit here. Hope it won't be the last. I will try to convince you that what we do is also related in some sense to the field of complex system that you all work on. And so yeah, it's a pleasure to talk to you about this work we've been doing recently about animal movements between farms and the propagation of livestock diseases among farms. So of course you can understand that this is, while this is a theoretical work that I will present, it has potentially a large number of implications, since livestock diseases are on the one hand a heavy economical burden, and on the other hand, many diseases that pass on to humans exist before in livestock. So there are communications between diseases of animals and diseases of humans. So controlling the livestock diseases is also very important in this respect. So my seminar will be divided mainly into two parts. In the first part, I will present you the data set that we use that describes the mobility of bovines in Italy. So as you may know, in Europe, since the mad cow disease crisis, it is requested by each country to have a register, a record of all the movements of farm animals. So it is a huge data set that is available, and you can track the animals really one by one. So it's really an example in which you have complete information. Unfortunately, countries do not communicate, which means that France has a register, Spain will have a register, Italy has a register, but when an animal comes from France to Italy, you know the farm where it arrived. If you're from the Italian side, you don't know the exact farm from where it originates. So you have some border issues sometimes, but I will talk here about the Italian bovine mobility network, on which we have the full information for a whole year. So I will talk to you about the statistical properties of this network, so about its dynamics, and some of the consequences, both theoretical and practical, that you have from the fact that this network is dynamically changing at a daily frame, at a daily time window. And then I will move on to the issue of spreading on a network which is not static, which is not fixed in time, but which is moving at the same rate, at the same velocity as the spreading itself. And of course, it raises new issues about how to understand the spreading of the disease and the role of the initial conditions, and how to define nodes that are in some sense more important than others, or maybe important between quotes, and that could maybe act as sentinels in a dynamical network. and I will finish with some conclusions on perspective. So first, the data set that we have consists of all the bovines moved between farms during one whole year. Actually now we have several years, but we were working here with 1 year, so 365 days. And we know, so for each animal, which with a daily resolution, between which farm it was moved on each day or where it was staying on each day. So you can transform that, of course, into a network which is both directed and weighted. So a link between I and J denotes the fact that some animals were transported from I to J, and the weight denotes the number of such animals. And of course, you can have transport in both directions of different animals, or you can have sometimes just fluxes in one direction. So this is a directed and weighted network. And in fact, it's not just one network, but it's 365 networks, because we have, as I was saying, the 1 day resolution. So the unit for me is a day. And we can have, for 1 day, a certain number of movements from between farms, and the other day other movements, etc., etc. So we have 365, let's say, snapshots of the movements. So we have a time order series of weighted directed networks between farms.
Excuse me, Alain.
Yeah.
Let me show my farms. Why do animals move from one farm to the other?
Because humans want them to. So,
why?
of course, you have in fact different types of farms. So some are in fact pastures, some are assembly centers, some are slaughterhouses where they arrive, they don't leave. You have markets also. So both animals can be sold from one farm to another. They can go to one place to be there for a few months for pasture, for instance. To have,
but to have an idea in order of magnitude, you were talking about 4 million cows, right? How many of them move in 1 day?
The total movement divided by 365.
We have, I have some data further on the dynamics of animals. I don't remember exactly, but maybe that will answer your question. So on each day, that is a partial answer, the network is very sparse for 1 day. So if you look at the number of farms that are sending or receiving animals on 1 day, it's very small with respect to the whole number of farms. If you aggregate on the whole year, then you have movements between all farms. So I will show some more data later on. So indeed, typically, the best resolution we have is on 1 day, but you can look at the network of all the movements during 1 week. So you aggregate all these movements between t and t plus 7, t plus 6. Or you can have during a whole month or during the whole year. So let's look at the statistical properties of this network to see how, let's say, one immediate question is how different are they from 1 day to the next, from 1 week to the next, from 1 month to the next, etc. And first, of course, we look at the statistical properties, like the distribution of the number of incoming or outgoing links, the number of distribution of the number of animals on one link, etc. So if we look at statistical properties, in fact, they are very, very stationary. Well, here you have the aggregate case, so you have just one network for 1 year. But for networks aggregated on a time window of 28 days, you have 12 or 13 such networks. And what you see here is that the red dots are the data for the network of one particular month, and in gray you have the network of the other months. And statistically, they are completely superimposed So it means that, and you can see that also for different statistical quantities, if you look at all these statistical distribution, let's say aggregated on the whole network, you obtain that they are very, very similar. And of course, they are different if you aggregate on 1 day, on 7 or longer time scales, because if you aggregate on more, on longer times, you will have a denser network, you will have more animals moved on the same link, etc.
What is the probability referred to what on the y-axis?
This is the probability that a certain link carries a certain number of animals, which is equal to W for 1 day. So here you can go until a couple of hundreds, but if you aggregate on more, you can have a much larger fluxes. So on the one hand, we have, statistically speaking, networks which look the same from one moment to another. However, we know that things are moving first on the network. So, for instance, this is the probability distribution of the number of displacement of one animal during 1 year, sorry. So you see that very, very rarely some animals reach 10 displacement, but this by no means a heavy tail. Most animals will move 2 or 3 times, maybe. We have also the length of the displacement, which once again is not particularly heavy tails. Most links correspond to 10, 20 kilometers, but sometimes you have also links that go very far. So you can have animals which are transported on very long distances.
This is aggregated in 1 year?
This is aggregated for 1 year, right? And what's also important is to look at the how long do animals remain in the same location between two displacements. So here you have something which is rather broad, but which depends then on the type of farm that you are talking about. So for a market, typically they should remain just a few days, while on a fattening farm or pasture, you will have typically peaks at 3 or 6 months, for instance. So you have distribution that have maybe a broad distribution, but however there exist some typical times which are due to the season, to the seasons, basically. So in any case, we know that there is some dynamics on the network because it's a transport network, so we are transporting animals. And of course that can be important when we think then about movements of diseases which can be transported by these animals. So if we look now at the properties of the network in terms of very simple quantities like the number of nodes, of links, or the size of the largest connected component, of course then we see that we have very strong fluctuations that are due to weekly patterns. For instance, on Sundays almost nothing is transported, but then you have also seasonal patterns that are clearly marked. So the network itself, even in some quantities, simple quantities that are just very broadly describing, shows that even if the statistics are the same, the network is changing. Now we can illustrate that even better by looking at snapshots of aggregated networks during 1 month. So here I don't show the whole network because it's very big. I just show, given a certain node, which nodes are distance at most 3 from this red dot. And this is taking into account all the movements that occurred during the month of February. Now I show the same network, same seen from the red dot at distance 3 in March and in April. And in fact, you see that the networks are very different in the sense that this node here is not at all the same as here, but it's the same as here. So it doesn't mean that in February or March, those nodes did not exist. It means that they were a distance larger than 3 from the red dots. So seen from anywhere in the network, the surroundings, let's say, change strongly from one month to the next. This, of course, just a pictorial illustration, but it shows to you that the structure itself of the network is not at all the same, even if statistical properties can be the same. And it already tells you that many measures, some mosquitoes, and mosquitoes tend to like me, and I don't like them. Sorry. Any kind of measure based on centralities or path will probably fluctuate a lot from one network to another. And in fact, that's what we so that the distribution of times during which a farm is active, which means sending animals on consecutive days, for instance, or inactive, and here you see rather broad distributions showing that you have some burstiness also in the network. So both this picture and this burstiness that is at work in the network, I will skip that, tells you that there will be some important fluctuations in the topology of the network. Moreover, we have also fluctuations in the weights of the network. Let's consider a link that is present at different days or at different weeks. And if we look now at the number of animals that are transported from in 1 week and in the next week, they can also fluctuate a lot. And in fact, if we look at quantities such as the ratio of the number of animals in 1 month divided by the number of animals in the previous one, well, you have distributions that are in fact similar to what occurs in firms' activity, in economic activity. So it's not very surprising, since in the end it's also an economic activity in some sense. So to go back to the issue of fluctuations, as I was saying, all this dynamical evolution at the level of the links that appear and disappear, the distribution of lifetime of the links and nodes, tells you that you expect fluctuation of various centrality measures. And here I just illustrate that for, so the strength is the number of animals that are sent out of a farm during 1 day, and you can rank the nodes according to the number of animals they have sent. And what you see is that if you rank them, on 1 day you can obtain a certain rank plot that gives you the strength as a function of the rank. But for each of these nodes, you can look at the fluctuations during the year, and you see that its strength fluctuates a lot between very small values and very large values. So in fact, this ranking is by no means stable. Nodes that are ranked very high in 1 day or in 1 week could be ranked very low in the next week. So this is a priori an issue, since we are used when considering networks to consider centrality measures which are computed on a static snapshot of the network to be very important. So what if I cannot actually rank the nodes, because if I rank them, then my ranking will not be good on the successive time. Of course, one could say, okay, maybe it's because we are considering the whole network and it's only a periphery which is varying a lot, and maybe you have a very strong backbone that is always there and very robust. Well, in fact, we have checked that, and by using the disparity filter introduced a couple of years ago by Serrano, Bugudi, and Respignani, in which for each node you look at its surrounding and you select the most statistically important links. So I will not give you the details on how this is done, but typically you do that for each node, and then you obtain a sub-graph of the original graph, which is called the backbone, and which you can compute for each network, be it weekly or monthly or daily network. And then you can look how does this backbone evolve from 1 month to the next. So first of all, you reduce a bit the fluctuations of the weights, which is kind of natural since in each case you are selecting the strongest links with respect to the surrounding of each node. But if you look now from at successive backbones here for different months, and you look at the overlap between backbones, so it's one, of course, between 1 month and the same month, but you see that if you look at the backbone of the first month and you look at the overlap with the backbone of the second month and the third month, fourth, etc., you see that the memory of this backbone is fading quite rapidly. So depending on the significance level of the backbone, you select smaller and smaller subsets. Here you have some memory for 2, 3, 4 months, but then it fades. So it means that even the most significant links in 1 month are only partially significant links in the next month, and if you wait like 6 months, they might not be significant at all. So you have an important fluctuation of the importance of nodes and links, not only from a part of the network which is not important, but also for the most important part at each month. So what are the immediate consequences of this dynamical character of the network, of these very strong fluctuations? Well, of course, it will have consequences when we look at dynamical processes on the network, and in particular if we try to understand which are the important sites in the network. So just to give you an example, let's look at the percolation analysis, which is very often used as a probe of networks and to classify the most important nodes and to show how some ranking methods can be used. Moreover, percolation analysis is also linked to the definition of strategies for disease containment, because what is percolation analysis basically is to look at a network and to start removing nodes from the network in a targeting manner or in a random manner, but here we will look at a targeting manner, so that you disconnect the network. And if you disconnect the network in some small parts, it means that information or disease cannot spread anymore from one part of the network to the other. So basically, it means that identifying the nodes that, if removed, breaks the network apart is also a good way to identify the nodes to vaccinate or look after more than the others in the case of a disease outbreak. So the percolation is analysis at the same time something rather theoretical to look at how networks are built, but it has also an importance for some practical strategies in disease containment. So here, let's assume we have a certain network at time t1, and then at time t2, let's say those are 2 successive months, we have a network that has changed. But we only have information about the network at time t1. So we are able basically to rank the nodes in at time t1 according to their importance. But then if we apply this strategy at time t2, what happens? So here we look at the largest degree nodes, which is an immediate measure of centrality, of importance, and we remove this node. And then we do the same at the next time. And then we look at the next largest degree node, and we remove it in both network, etc. And we see immediately that, of course, at time t1, this strategy was efficient because we have the information about the degrees, and so we can break the network in small pieces. But the network at time t2 has not been broken simply because the high degree nodes at time t1 might not be the high degree nodes at time t2. And in fact, if we look effectively at what what happens in our bovine displacement network, this is exactly what we obtain. So here we look at the largest connected component remaining after we have removed a certain fraction of nodes in the order of decreasing degree. And we see that if we do that on the network at time t1, after removing a small fraction of the nodes, have completely broken my network. But if I remove the same nodes in the same order in the next month network, then it's much, much less efficient. So of course, this tells you that indeed, if you base yourself on past or static information, it might not be very effective. So once we know that, we know in some sense that we have to look a bit better at what happens in spreading phenomena in this kind of networks, and take into account both the dynamics of the network and the dynamics of the spreading phenomenon. So I will here show three aspects. First, the effect of the time scale we use for the description of the network. Then, how do we understand the effect of initial conditions, of different initial conditions in the network? How do we measure that? And how can we determine the important nodes? Because, as I was showing here, if I have just information for a certain month, then it's not enough to understand. I mean, it's not enough to tell you that those nodes that are important at a certain time will still be important at the next time. So how to determine these important nodes, and how, in fact, we have to shift from a perspective in which we can just look at the network and decide which are the nodes that are most important, to a perspective in which we have to take into account at the same time the dynamical phenomenon we are studying on the network and the dynamics of the network itself. So in this sense, important might be relative to the type of phenomenon we are studying. It might not be important nodes per se in the network. So here we will use a net spreading phenomenon, which is partially a toy model, but which has some important elements of realism, as we will see, in which we have nodes that can be divided into susceptible, infected, and recovered or removed. So infected nodes can propagate the infection to another node. So here B is infectious, and we have this network at time t, and at the successive time, B will have infected C, okay? And then we have a link from B to D, so B can infect D, and then D will have recovered after a certain time. So here we consider, in the network we have, the nodes are farms. So you could say, okay, this is not realistic because the farm is not infected, it's one animal in the farm. Now in livestock diseases, it is very often considered that once an animal arrives in the farm, the contagion is very, very fast because the animals are close to each other, and the transmission between animals is usually rather fast. So in most models, contrarily to human diseases, one really considers the farm as a unit for the propagation. And so, moreover, it's also true that if one animal is found ill on a farm, and if the only, then the measures will be either vaccination or eradication of the animals, and the whole farm will be, all the animals on the farm will be killed, usually, or vaccinated, depending on the illness. But so it's when dealing with livestock diseases, it's very common to consider the whole farm, contrary to what happens in humans, in which, for instance, if A would be a town and B another town, you can have one person infected among thousands. So let's look now at all the possible initial conditions And let's look at what occurs when we do these simulations on the networks aggregated over different time windows. So if we look first at simulations on the network that is dynamical, which is really this point with delta t equal 1 day. So you see that depending on the initial conditions, here we look at the number of the epidemic curve, which is the number of infected farms versus time, and we can clearly have profiles that are very, very different. Now, if we look at larger and larger aggregations, so here it's the aggregation over the whole year, first of all, you see that the scale of the epidemics is not at all the same. So the reason is that if you aggregate more the network, you have more links, so the disease can propagate more freely on the network and can reach many more farms. Well, here, for instance, the disease is not reaching A and is reaching E quite late, while if you had aggregated everything, then B would be able to contaminate E directly. So here we have a clear first effect of the aggregation of the network, which already tells you that if you want to simulate and understand this kind of propagation phenomena, you have to use all the dynamical temporal resolution you can, and you cannot rely on just having the global set of movements on 1 year. Now, clearly, this process is entangled with, as I was saying, with the system dynamics, and different initial conditions can give very different patterns. So, is there here some hidden patterns, some hidden robustness that we can detect? Is there some geographical effect that we can detect? Well, to do that, the method we have used is to define the initial condition similarity network, which is defined as follows. So let's consider an initial condition, so it's an initially infected farm, and we do the spreading, so it's deterministic, and we can look at the invasion path of I. So the invasion path is composed by all the farms that have been infected due to the fact that I was the initially infected farm. We can do that for each possible seeding farm, and we have one invasion path for each initial condition. Now, if we look at two different initial conditions, you can look at how similar are those invasion paths. And you can look here at the nodes which were common to these two invasion paths, and you can define a measure of similarity between these initial conditions, which is just the ratio of the common nodes divided by the union. So if this ratio is equal to 1, it means that the path, exactly those two initial conditions led to exactly the same set of farms which were infected. And if it is 0, it means that I and J determine two completely different epidemics. We can do that for each pair of initial conditions, and then a simple thresholding, removing all the links with small overlap, will define, in fact, will separate these initial condition similarity networks into different clusters. And this simple thresholding actually leads to the emergence of clusters, and here each cluster is denoted by a different color. And we first see that there are some geographical effects. I mean, some clusters are localized in a given geographical area, but other clusters are much more dispersed, and also we see that geographical regions can in fact overlap. So there is sometimes some effect of geography, but it's not very clear. I mean, you cannot say a priori that nodes in the same geographical region will lead to similar epidemics. That's the first information. Moreover, if we look at the nodes which are in the same clusters or which lead to similar epidemics, we see that in fact they do not share many links in the original transport network. So they are not like communities. You cannot understand these clusters of initial condition by looking for communities or tightly linked groups of nodes in the transport network. What this means is that you cannot detect these clusters by looking at the network itself. You have to look at the network plus the spreading phenomenon. Moreover, if we now separate these clusters, this should read cluster and not community, as I was saying, those are not community in the sense of network communities, and you look at the spreading pattern for each of these initial conditions in the same cluster, you see that these very kind of chaotic patterns actually separate very nicely, and so the same nodes which are in the same cluster will lead to the same timing for the epidemic spreading and very similar spreading curves. So it means that indeed, if we know the cluster from where the epidemic starts, we know when will be the epidemic peak, whereas here we had something very ruffled, very messed up. So those clusters are indeed classifying the spreading patterns into different well-separated classes. Now, if I have a node in the network, I want to understand not only if it is part of a cluster of initial condition, but what happens if I detect that it is that there are contaminated animals in this farm. So a first way of characterizing the role of a node with respect to a spreading pattern, so spreading phenomenon, is the number of times that it will be infected. So for instance, there are some nodes which will be infected very rarely, some other nodes which will be infected many times as a function of who is the initially infected node. So in static networks, this would be typically a large degree node, this would be a small degree node. So as I was saying before, it's maybe more complicated than that. And moreover, I want to know for each node from how many different clusters it was infected. Why is that? I was saying just before that if I know the origin in which cluster the spreading originated, then I have interesting information about the spreading. So for instance, if I have a node which is infected always by the same cluster, which it means that I can be sure if I see this node, if I see an infected animal here, that the epidemics originated from here, and then it means that I have information about what's happening, what will happen in the future. If on the other hand I have a node which could be infected by many different clusters, then it is less interesting because I have much less information on the origin of the disease. And so I have much less information on what will happen next. So it's possible, in fact, to define what we call a Cedar uncertainty, which basically tells us that, which basically is 1 if the node is equally infected by all clusters, so I have a total indetermination about the initial condition, and it's 0 in this case in which I know with certainty where the disease originated from. And so for each node, I can put each node in a 2-dimensional plot in which I put on one axis the number of times it was infected, and on the y-axis I put this uncertainty. And I will define sentinel nodes that are often infected and which have a relatively low CEDAR uncertainty. Why? Because it means that they have a good probability to be infected if there is some spreading phenomenon occurring on the network. And if I know they have been infected, then I have a lower uncertainty on the initial condition on the spreading. So in fact, we define these sentinels as nodes that remain in this area for various initial times as well. And what we see is that the number of nodes that we define as sentinel is very small. In fact, it will depend, of course, on the precise bounds I put here, but typically it's rather small, and with a relatively small number of sentinels, we will in fact detect a large fraction of the outbreaks that are of size at least 10 or 20. Moreover, if I look at the outbreaks I detect, I see that for most of them, I will detect them relatively early, because of course if I detect the outbreak when it is over, that's less interesting. And here, for most cases, we will detect the outbreaks in the first third of the outbreak unfolding. Now, I don't have the picture here. I should add it. Another interesting point is that these sentinels. I mean, we had the question actually by a referee, but these sentinels, can you tell them in advance without looking at spreading, just by looking at the fluxes of animals? Like, are those just nodes with very high traffic? And in fact, if we look at their traffic and their number of connections, some have very high traffic, but some have very low traffic. So they are in fact spread out on very different traffic and connection number values, and so they cannot be detected a priori just from the data on the network. You have to detect them using also the spreading phenomenon. So I would just conclude by emphasizing once again that so in dynamical networks you really have to look at the dynamics of the network to define new centrality and importance node quantities. And in fact, I think that the identification of these important nodes will depend on the dynamical phenomenon you are looking at. You cannot just look at the network topological perspective. And just as what is the ongoing work on this issue is to look at successive years to see if we have patterns from one year to the next, and also to define a bit more how we can identify. I mean, it's a good thing to say we have a low uncertainty, but then you have to do the reverse engineering task, which is if I tell you this farm is infected, what are the most probable initial conditions? So if the uncertainty is 0, it's easy. But if the uncertainty is 0.3 or something, you have to do devise an algorithm in some sense to run the most probable initial conditions. And so I want to thank you for your attention, give you 2 references, and emphasize that this work was mostly done by Barrat, who was at that time PhD student, under the supervision of Vittorio Colizza and myself, and in close collaboration with Fabrizio Natale and Lars Salini in Italy. Thank you for your attention.
Okay, so well, let's start with the questions. Well, I mean, the usual thing is that students first, so I don't know if is there any question on that side? That's a yes.
So I have a question about the clustering. How much you did doing? So how was it done? What, for instance, what kind of time series of networks have you used? Have you used daily networks or?
Yes, yes, because we have shown first just by a pictorial, just by looking at the incidence curves, that if you start aggregating, then you lose a lot of information. So in this simulation, you have to use the daily network.
And for instance, you performed just one step of the SIR model for each day, or many steps? Because I guess this would affect as well.
Right. So we have the daily resolution. So it means that if a farm is connected to another farm on a certain day, it can infect this farm, and that's all. I mean, you cannot propagate 2 steps in one day.
Okay, and then you just were taking consecutive steps and calculating those overlaps of infected nodes to get the clusters.
So to get we compute for each initial condition, you run the whole simulation until the disease dies, and it gives you all the farms that have been infected. Due to the fact that this one was initially infected. This is given a starting date.
And then, okay, so then you take minus starting case, and that's how you calculate the overlaps. It's like average overlap.
Well, it's the number of common nodes between these 2 equations. So if you have 2 different infected nodes, do they have the same consequence or completely different consequences?
Or you will start from the same day, from day 0?
Right, this is starting from, then we looked at, so I didn't talk about that, but we looked at the stability of this cluster when we changed the data. It depends. Some are stable, some are, so we classify also the cluster according to the stability. I didn't talk about that. Define the quantity which tells you. And we have very different types of clusters. Some are completely unstable and some are very stable.
And what is the deterministic version of the SIR?
Right.
Did you do the stochastically?
So that we did it as well. We did the extension to stochastics. And well, it works quite well as we have basically the same phenomenology, but of course for each, first of all, it's computationally much heavier because you have stochastic infection tree. And for instance, this is what we obtain for certain transmission rate. And you see that each curve now has some fluctuations. And so of course, you have stronger fluctuations, but for instance, you see that those clusters they still get same timing, same shape of curves.
Do you have any hope that the epidemic part that you mentioned, I mean, you can get some information that allows to predict in, let's say, in a foot and mouth epidemic that was, I think, something like 2001. I remember reading some paper in which, I mean, there were several strategies in the UK of, I don't know, I mean, killing, slaughtering all the animals in one farm, or having some security margin with some kilometers. Do you think your data, your model?
Well, hopefully, I would say hopefully yes, in the sense that the strategies that have been used in this crisis were mostly based on geographical proximity, and also the models that have been run afterwards and validated. Basically, you have a kernel of transmission between one farm and the other, which just is a decaying function of the distance, and plus some complicated kernel depending on the number of each type of animals in one farm and the probabilities to contaminate, etc. But they are not taking into account the dynamics of the networks. It's, I mean, that was already a few years ago, but I think this is overlooking something important. So yeah, here at least I think redoing this kind of, and also in the veterinary literature, you have some network analysis, but usually they take the movements on 1 year. and they look at then targeted removal, and they say, okay, you have to look for the heavy traffic ones, etc. Yeah, it's important progress is to make in this direction.
Yeah, and apart from this model, I mean, I see that if you introduce the stochasticity, you get that some of the clusters are more, let's say, change more the trajectory that you use than others. But what happens if you change the model? Like, for instance, instead of the SC, you use the IR, you use this IR.
I don't know, we didn't check.
Okay. So the idea was to ask how much is the world clusters with respect to the the other thing is then, I mean, the sentinels are good to warn you that there is something moving in there, also that there is some disease. Are they also good, for instance, for stopping the disease or not? So there will be some kind of intervention you can do based on this kind of information?
Well, the idea would be that if you manage to have an information on the cluster where you have the initial condition, it means you have really good information on the most probable invasion path, which means that you will be able to target more effectively the farms where to control and eventually vaccination or slaughter. So instead of, let's say, saying, okay, I have this, of following, and each time you have some detected animal, you have to control and then to eradicate in a certain, like say 10 kilometers, whatever, you can move a bit ahead. You can gain time. The idea here is always to gain time with respect to the propagation itself. And if you can target a subset of farms, even sometimes, I mean, some of these things are very far apart. So it means instead of just looking in the region, you can say, okay, I know, I detect here, but it might have been already propagated, and then I know how to target more easily.
One of the nice things in the simplest network approaches to this kind of spreading is that it was relatively simple. And the usual approach, you look at the network of the change between farms and the global aggregate one. Okay, this has lots of traffic. This is the most important. So it's simple and easy, but you say it's wrong. Then you now what you are doing essentially is to simulate in the real moving network some model of the real disease. And you detect what are the important nodes by following the actual path of the disease. But for every disease and in every country and every year, you should repeat the full simulation. And from this, can you get anything general to say to someone, this is the important point, this is not important? Or just you have to follow exactly the full dynamics for every case?
May I add to the question?
Yeah.
I mean, analyzing the data you have, you conclude that the dynamics of the network is very important, which makes sense. Now, can one try to make some model of the dynamics of the network such that one can get some general result?
Okay. So those are actually two different questions. So from your question, the answer is yes, you need the data and you need to run the simulation. So one hope is that from one year to another you will have strong similarity, because here we have like seasonal effects, etc., which should be the same from one year to another. However, if you have data from a different country, then it looks like you cannot just look at the data and say this is important. That's my point. Now, of course, as I was saying, some of the sentinels do have large traffic, but not all of them. So if you want to optimize the trust, of course, if you have unlimited means, then you can start by looking at the most heavy traffic. But it's not I'm not saying it's wrong, I'm saying it's not optimal. And you are overlooking some important parts. Now, from the point of modeling, we are actually working currently on writing a paper on the model, quite simple model, which was inspired by our study of this network, and in fact, which was inspired by some properties I did not mention, but basically, which is that the network is created by something moving, and so each bovine is defining a path between nodes, and so we are taking this path as building blocks of the network, and we obtain some a model dynamical networks which has the same phenomenology, and in which you can tune many properties. So that's one of the roles of modeling, I think, which is to provide networks in which you can tune properties and then study what determines maybe the importance. Here we have, it's 365 snapshots, but it's still one sample. So it's important to do this modeling task. So hopefully it will, in the next month, we started writing.
Okay, so is any question? If not, let's thank the speaker again.